right? Everyone is here. So, good afternoon. My name is Gurpreet Singh. I'm from Kansas State University, and I'm the principal investigator on the National Science Foundation PIRE project. And so, because this workshop is being organized in conjunction with the MATCOM or COMMAT project in Germany, we have a slightly different audience. So, I'll provide an overview of what an NSF PIRE project is, and then also offer you results from the past 1 year from Kansas State University. Okay. So, what is NSF PIRE? So the PIRE stands for Partnership for International Research and Education. This is a program run by National Science Foundation Office of International Science and Engineering. And this is different from regular NSF proposed projects because it's specifically geared toward international activities supporting all disciplines, not just pure science or engineering, but also social science. So every 2 years, they award roughly 10 to 14 projects. And we were one of the 14 in 2017. So this is a 5-year effort within the final year. In the past 4 years, NSF has not made any award under PIRE. So typically the award amount is 4 to 5 million. We were awarded 4.69 million for a period of 5 years, which roughly translates to 6 PhD students and 25 undergraduate students. So I would say a bit different from your COMMAT or MATCOM because we are more toward undergraduate education. And I believe your project is roughly 9 years. It can be 9 years. For us, it's 5 years. Then the question is, why partnerships for international research and education in polymer-derived ceramic materials, right? I believe there were at least 2 very compelling reasons why we got this awarded. One is just the fact that the universities in the US, they are lagging behind Europe and Asia when it comes to pre-ceramic polymer chemistry and especially fiber processing. If you look at this map, this is in the red one are the universities that were conducting PDC research in 2017, just a handful of professors conducting research in PDCs and also teaching courses related to. So there was a need for that, right? And the second is the implementation of ceramic matrix composites in GE LEAP engine, which allowed operation of the gas turbine engine at elevated temperature, which means better fuel burn efficiency. So approximately 15% improvement in fuel burn efficiency. What this means? This means that industry is going to need university-trained professionals, and that's where we come in. Because as the market for CMC grows, there'll be need for trained professionals. So I think these were the 2 compelling reasons why we got this project funded. Then the question is, what is this? What does it consist of? So the R here stands for research and E for education. So like I said, it's not a typical Department of Defense or NSF project. Process need to be both on research and education. So what we had done is we had 3 thrust areas in research and 3 education themes. And the 3 thrust areas are focused on, the polymer state, where we work on identifying pre-ceramic polymers and looking at their rheological properties and ability to draw fibers from. And then the second one is the ceramic state, where the polymer fiber is undergoing this organic to inorganic transformation. And then assessing the mechanical and thermal properties of the fiber material for use in ceramic matrix composite. And so we have experts in each of these 3 thrust areas. So they're listed over there. I hope you're able to see. But that's where the Europeans come in. So we have 5+ countries involved with expertise in polymer state, ceramic state, and also mechanical and thermal testing. And on the education side, we have 3 thrust areas. So like I said, this is more undergraduate focused. So there is a student exchange program or dual degree program just to improve the quality of the graduate program. Graduate student experience, and then these short courses and annual workshop where we are here today. And so both need to be pursued in parallel. Then this slide here shows the progress and the themes for this NSF project over the past 4 to 5 years. So in the beginning, we were just, like I said, these pre-ceramic polymers are not readily available in the US. So, so our initial focus was to just source whatever we could find from the market and also from our collaborators in Germany and France. So we looked at understanding the rheology as well as the spinnability aspect, and we realized very quickly that the large majority of these oligomers or short polymers are not readily spinnable in their pristine form. One way you can tune the rheology is by inducing some sort of a thermal cross-linking, but generally those reactions are not very controllable. So the change in viscosity is rather sudden, and so there's very little opportunity to draw fibers from these oligomers in their pristine form. So the first year of the project, my student was based on review of literature, was able to introduce some sort of a spinning agent. The spinning agent is generally some sort of a linear organic polymer. So he was able to just draw fibers by hand. And in the following year, we were able to produce fibers, non-woven fibers or fiber mats. And in the last year, we have ventured into other kind of pre-ceramic polymers. These are linear ones, linear siloxanes, the 3 that you see here. This is again based on review of literature, where there is some evidence that it's relatively easy to draw fibers from linear oligomer rather than a branched or cyclic one. And indeed, in this case, we were able to minimize the amount of organic polymer in the solution. And then in the last year or so, I have another PhD student who is looking at introduction of high strength fillers into the PDC fiber. So specifically boron nitride or other kind of 2D materials that are able to sustain high temperature and also able to offer improved mechanical strength. So this is again based on review of literature. This is from a paper in Science magazine in 2020, in which the authors introduced exfoliated graphite or graphene at very low weight loadings, roughly 0.078%, and thereby able to show improvement in strength as well as modulus by 2 to 5-fold. Okay. So in our case, graphene would not work because it burns at roughly 400 degrees C. So we are looking at other kind of 2D materials that are analogous to graphene and still offer, improved mechanical properties. Also in the last year, and then we are also looking at what to pursue beyond PIRE. So we have shifted focus towards ceramic matrix material rather than just working on the fibers. This is again based on 2 aspects. One of which is just the language that is coming out from the funding agencies in the US. It seems to me that there's increased emphasis on just coming up with better, faster methods for making CMCs. And not just CMCs, but CMCs that are providing properties consistently and repeatedly. So that's one challenge that is identified by most US government funding agencies. And the second one is that these PDC fibers or silicon carbide fibers, it seems to me that they are more readily available now compared to 5 years ago. So there are some new companies who are offering silicon carbide fibers. I'm not sure how good they are, but they are available. And this is something I've learned from my conversations with industry partners. So they would rather have us focus on interfacial coatings, for example, or just making better CMCs. Also, based on my interactions with young scientists, I realized that there's much more interest in 3D printing, for example, of PDC materials. And not just that, but also failure modeling, prediction, and design by use of artificial intelligence or machine learning. So I believe that is going to be the future. So in the final year of the project, we have, like I said, we have made this pivot towards CMC materials. So I have 4 or 5 PhD, 4 or 5 undergraduate students who are working, and also a couple of PhD students who are now looking at CMCs. So we are able to, and this is not just Kansas State University, but also University of Colorado. So what we are doing is we are learning how to make mini composite bundles using carbon fibers or silicon carbide fibers, for example, and the matrix is generally silicon oxycarbide. And then developing tools for assessing mechanical properties of such mini composite bundles, followed by electron microscopy and also X-ray micro-CT. X-ray micro-CT allows you to look at the here inside of a specimen. There's one example here from Ali Badran's work, and he's going to be talking about this in tomorrow's presentation. So these are the undergraduate students who have worked with us in the last 1 year. And like I said, we have two kinds. One kind is working when the school is on. The other kind of student is undergraduate student, is called them PIRE summer scholars. These are students who just specifically working over the summer. And these students, I'll just briefly talk about their projects. So Mohammed Rasheed is a senior in mechanical engineering. And most of the time, these undergraduate students are assigned to senior undergraduate student or a PhD student. And so these undergrads are generally doing repetitive work, which a PhD student finds boring. But for an undergrad, it's an opportunity. So Mohammed's work involved just making this CMC bundle and then assessing, the wettability, for example, of the fiber by the precursor, and also just assessing the usability of this kind of a cardboard type tensile test method. This is a method that is typically used for testing mechanical strength. It's a very crude method, but it still works for individual fibers. We wanted to check if such kind of method be applicable to mechanical testing of CMC bundles. So Mohammed would just keep testing these samples, look at the scatter in the data, get averages, standard deviation, for example. And he's not here today because he's also enrolled in summer classes. Yeah. Another student who worked with us, Jessica, she's an undergrad in chemical engineering. We get students from all disciplines. Jessica was primarily responsible for producing cross-linked siloxanes. So these are the three siloxanes I briefly talked to you about. They are very unique in the sense that they have a high oligomer to cross-linked polymer yield. So roughly 80 to 90% would cross-link. And then when we go from cross-linked polymer to the ceramic state, these have very low ceramic yield. So we were interested in knowing what would be the reason for that. And so in order to do that, you need to have some sort of a TGA mass spec, for example, or bulk composition analysis. That requires hundreds of milligrams of the material. So this undergrad was basically just crossing them in parallel, then in large quantity. But this material has been shared with our partner at Arizona State University. They have expertise in HT colorimetry, and also PGA mass spec. So we will hear from this graduate student Jackson in tomorrow's presentation, tomorrow's session. And then one other undergraduate student, Alison, and her job was to conduct electrospinning of silicon oxycarbide fiber mats and then use them as a filler phase in photoresins. So she would 3D print epoxy composites and then assess the mechanical properties. And these were samples produced at very weight loading. And then we are also looking at silicon-based photopolymers. So these are sourced from our partners in France. By the way, this student is also not here because she is pursuing internship with PIRE in Kansas City. And the previous student here is interning for Philips 66. And they pay much more than what we do. So it's a but anyway, they will be back in the fall term. And then student visits, we had two students from Professor Peter Kroll's lab from University of Texas, Arlington. This is one of the important aspects of the PIRE project, is exchange visits are encouraged. So these are students who were interested in learning electrospinning processes, and they had their own pre-ceramic polymer, which they wanted to study. And so I had a PhD student, Eloisa, she trained them on the electrospinning, as well as electron microscopy of these specimens. Now, one of these students here, Takhya, is working with Professor Gunther Motz at University of PIRE, and you will hear from her in, I think it's her presentation is tomorrow. Okay, so then that, and then we also had a PhD student, Jerson, visit us for a week. This student was primarily involved in applying spectroscopy to the pre-ceramic polymers and learning polymer to ceramic transformations, but also mechanical testing of CMC bundles. And so based on this students' collaboration with my PhD student, we got this paper out. This is just, you can see it came out in June. And in this work, Gerson was able to correlate the thermal stability of the commercial silicon carbide fibers with the mixed bonding character, or the amount of, or the level of mixed bonding in the fiber, and also with the mechanical property, for example, modulus of the fiber, by employing HT coloring. So you will also, I encourage you to take a look at this paper. Then we had 3 international students visiting in 2021. One student here is from IIT Madras in India, Professor Ravi Kumar's group, and his project involved just developing single-source precursor for making niobium-containing and titanium-containing silicon oxycarbides. Now, some of you may already know this, but introduction of titanium or niobium into SiOC may alter its electronic structure, thereby allowing you to tune electrical property, for example, electrical conductivity. So he's interested in learning that. And then we had one student from Brazil, Eloisa. She's a PhD student of Professor Machado. She also spent time at University of Barnett with Professor Gunther Motz for 1 year. And this student was not directly funded by PIRE, but she ended up helping our students, and her expertise in melt spinning of silicon carbon nitride fibers. And one more student from University of Campinas in Brazil. Her expertise is in in situ spectroscopy or in operando spectroscopy of carbonaceous materials, and that is something of interest when the polymer is thermally cross-linking and transforming into ceramic. So, and these students' stories were highlighted in the Office of International Program magazine. So this shows that we don't work in isolation, and if there's a good camaraderie between the project partners, and we learn from each other. So these are some of the papers that have come out from our group. This is just from Kansas State University. I did not have space to include Peter Kroll's paper or Alexander Rossi's paper. Generally, we aim for 3 to 4 full-length papers per graduate student. And these are some of the conference presentations. You can see the students have presented at ICACC and prestigious MRS meetings. Now I'll move on to the broader impact. This is a National Science Foundation, so there are 2 ways they evaluate success of a program. One is the intellectual merit, which is just research, and second one is broader impact, which involves benefits to the society, industry, development of curriculum, for example, and also just promotion of PDC materials, for example, PDC science. So here, they look at how many students have graduated and where they are at. So these are the students who, students who graduated until last year. And so you can see that 3 were fully funded through NSF PIRE Project, and 3 were partially funded. And this funding cycle, we have 2 more PhDs. One is Ali Badran from University of Colorado, sitting right there. And he has accepted a full-time position with GE, so he's now with GE. And he was awarded the best paper award. His work was awarded the best paper award last year. And then Shakir bin Wajib, he's my PhD student. He's no longer a student. He has finished his degree, and he was awarded the Outstanding Graduate Research Assistant in the department. Yeah. Then, who are our students right now? So these are the students. You will see some of them here. Sanjoy is working with me. He's the one who's looking at making these composite PDC fibers. Spencer, where is Spencer? Spencer is a superstar. He's our lucky, he's a lottery ticket. Spencer started with us as an undergraduate student and decided to pursue people. He has already started a company, okay? And that's why I'm calling him the lottery ticket, because if he is able to make something that is commercially viable, then we have recovered our money. The government has recovered money, right? The investment. And then Joel Garcia is a new PhD student at Lehigh University. And what they are doing at Lehigh is very interesting. They have an environmental XPS, so that in which you can subject your specimen to either heat or heat in presence of oxygen, thereby look at the surface product formed on the surface of the PDC specimen. Okay. So he is going to be presenting tomorrow. And then Sharik and Akshada, they are with Professor Peter Kroll, and Sharik is the computation modeling expert. Akshada is an experimentalist. And then Jerson Linnell, he's a PhD student, second year, he completed 2 years already with Alison Holthaus, expertise in HT calorimetry. And then Kendall Hendricks, where is Kendall? Yeah, so Kendall is Professor Kroll, and she is currently spending time at University of Trento working with Professor Giannis Soraru. Okay. This is the schedule. Skip this one. The superstars, the undergraduate summer scholars, right? So we must have 5 of these every year. So from my side, you have Hildana. Hildana was supposed to graduate last semester, but when I presented this opportunity to her, she decided to extend. She had many full-time job opportunities, but this is just too important. So she said, delay my graduation by 3 months. Then Henry Price is here. Henry spent time at University of Montpellier, conducting additive manufacturing of pre-ceramic polymers, right, with the crystal salami. And then Takhya, Holley, as I already mentioned, she's at University of PIRE working with most. And then Jonathan Kroll. Where is Jonathan Kroll? He's our returning undergraduate PIRE scholar. This year, he spent time at Polymer Institute working with Emmanuel and his group. And then Kushi Pandey, where is Kushi? Here, she is an undergraduate student of Professor Nabrotsky, and she worked with Gabby on nanodiamonds, I believe, or composites made from PDC materials. Then, just very briefly, where are the students from last year? So these are a couple of students who worked with me last year. They have since graduated, and both these girls have they've been hired. So one lady is working for Honeywell. Her project involved PDC coating on quartz fibers, and then Marin is working for Burns and McDonnell, which is a very large private company involved in energy space and manufacturing and construction. And both these students were recognized as the outstanding graduating seniors by our department in the spring term. Another important aspect of this PIRE project is how do we take the research that we do in the lab into the classroom? Generally, there is a disconnect. A PhD student work in isolation. So we are encouraged to introduce some of the research outcomes into the existing curriculum or develop new courses. So for the first 3 years, 4 years, I was just simply introducing lab modules into a course that I've been teaching for past 5+ years, Introduction to Composites. So the first year, I introduced 3D printing of fiber reinforced composite and then metal matrix composites. So these are hands-on activities which undergraduates like. And then the COVID year, but the first year of the COVID, we had to work toward some sort of FEA modeling. So there we were using ANSYS for fiber matrix analysis in CMCs. And then what I've done in the last year or this current year is introduce design courses. So there's in the final year of your degree, I believe it's similar here, students have to work on some sort of an industry or a design project, especially if you're a mechanical engineer. So what we have done is I introduced at least 2 projects where we assigned five undergraduate students. So one project involved just designing a text picture in order to assess the interlaminar shear strength of ceramic matrix composites. As you know, the CMCs are generally very weak in the transverse direction. And so these students designed these text pictures and then also conducted some experiments on PMC. And then the other project involved designing a 3-point bend test fixture for CMC bundles. Because these mini composites are much smaller compared to, these are not regular size specimens. And so we had to design a special kind of fixture. Right, and then, how are we managing? I would say this year is much more difficult compared to the first year of the pandemic, primarily because of the travel chaos. And however, I'm grateful to the our partners in Europe and Asia who have welcomed our students with open arms. And it's I must admit that this PIRE project is more like a one-way collaboration where we get a lot more help from the Europeans than what we offer. So I appreciate that. The sample exchange have continued. We still have having our Zoom meetings, but I just wanted to recognize these individuals here who have helped us over the past 5 years. And then another thing we are involved in is just promotion of PDC science by organizing joint track or symposia at national and international conferences. So this one here is worth mentioning. This is from 2021. This was organized by Matt Peterson of Air Force Research Lab, and Gunther, myself, and Paulo were co-organizers. It was very well attended. And then upcoming, we have the MSc Congress. So these are the partners here, from the PIRE. And then one more next year, which is the International Symposium on Inorganic and Environmental Materials. And there you see Samuel Barnett, with our PIRE partners, listed as the International Advisory Board member. These are the milestones. So when you submit a proposal to a funding agency, you have to offer some sort of timeline. And I believe these are the three research trust areas, education area. And I believe we have made good progress in research trust area 1 and 2. What we're lagging behind is the research trust area 3, which involves high temperature mechanical testing. That's primarily because we just do not have the equipment to conduct these kind of experiments, and it's really difficult to get access to the national labs who are not very keen on taking undergraduate students, because of the COVID. So our plan is to just simply do maybe ex situ testing, so just subject the specimen to elevated temperatures and then conduct that, and then the microscopy, for example. So yeah, that's that. And I think with this, I would like to thank the National Science Foundation for providing us this money. But more importantly, Professor Ralph Riedel, he is one of those very few individuals who understands science at its core, but also a very good leader and manager. So one must be able to overcome, mind must be able to overcome feelings. And so he is one of those individuals. He has been a great mentor to many of us. So we thank him, and thank you, everybody. So I believe, any questions? We have a couple of minutes, and before Ralph starts his presentation. Questions? This was, we'll have opportunity to interact later. But all of these projects that I talked about, we will hear from the students. So I wanted to not steal the limelight from them, let them discuss the